Here is an introduction to stellar remnants to accompany chapter 23 of the textbook Astronomy from Open Stax. So when we talk about stellar remnants, we've discussed these a bit in the low mass and high mass stellar evolution videos, but here it's all kind of shown together comprehensively in one picture. So we have a flow chart of stellar evolution starting from a gas cloud collapsing, and then you can branch things into whether something's low mass or high mass. The low mass stars, these ultimately result in things called a white dwarf that we'll talk about more in a little bit. And in the high mass star, you can produce a neutron star or a black hole. You can also explode and leave nothing at all, but that wouldn't really be a remnant. And so these are kind of our three remnants that we're talking about, white dwarfs, neutron stars, and black holes. One thing that wasn't touched upon in the low mass and high mass stellar evolution videos is the story that we told about how that evolution proceeds is mostly true, but it can be complicated by binary evolution. So most stars are actually in binary systems. In this case, the sun's kind of an exception. Not a major exception, but it's in the minority. And you can have things like stars interacting in terms of their envelopes interacting, and that changes the process a little bit. But nonetheless, in the end, you can wind up with a white dwarf, a neutron star, or a black hole. So let's start with white dwarfs. So this is the remnant that's left behind from a low mass star evolving. So if we look at our Hertzsprung-Russell diagram and the low mass stellar evolution video, we saw that our low mass star at the end of its evolution, when it blows off the envelope as a planetary nebula, it goes takes this fun path along the HR diagram, and it ultimately winds up here as this relatively dim blue thing. So a very hot surface, but very dim. So that white dwarf is roughly an Earth-sized object, and the mass is around the mass of the sun, right? So that's pretty compact. So it's 100 times or so smaller than the sun, but around the same mass. And because it's such high density, the matter is degenerate, and specifically it's electron degenerate. What that means is that the pressure that is supporting the star from contracting, so there's gravity pulling inwards, the pressure that's pushing outwards is just this so-called electron degeneracy pressure. It's essentially the pressure you get when you pack electrons very close together. And this degeneracy leads to a really interesting relationship between the mass and the radius. So naively, you might think if you have an object and you add some mass to it, the radius would get larger, right? You add more mass, it would increase in volume. But here, the opposite would happen. So if you took a white dwarf and you were to somehow add some mass to it, then you would actually decrease in radius. So this is a plot of the radius versus the mass, and you'd follow this green curve here. Now really what we see is white dwarfs often aren't gaining much in mass at all. Instead, you create white dwarfs with various amounts of initial mass, depending on the stellar evolution history. And so your population then follows this mass radius curve here. And the reason that it plunges at this around 1.4 solar masses is at that point electron degeneracy pressure is no longer enough, and this thing will wind up exploding, as we'll talk about in a moment. As far as what happens to this white dwarf, if it's isolated, then it will just continue to cool over time. So if we were to follow our white dwarf on the HR diagram, we have the luminosity versus the temperature. It would follow one of these blue curves here, depending on the mass. And when we take a look at basically all the white dwarfs that we can see in a large survey, then they populate this line because there are many different white dwarfs. They started out with some different initial masses, but not too different. And some of them are further along in cooling than others. So basically for each one of these dots, they would have started up here on this blue line and made it down to wherever it is that they're at. So they become just dimmer and redder as time goes on. One thing that's really interesting is there's a prediction that was long-standing and finally proved just a couple of years ago that cooling actually stalls at a certain point. So you don't just follow this blue line at the same rate, cooling at the same rate over time. You actually stall in this orange region. So depending on which blue line you're on, which is determined by your initial white dwarf mass, depending which blue line you're on, you're going to stall in this orange region, and that's due to the white dwarf crystallizing. So it essentially goes from some amorphous configuration, some amorphous carbon-oxygen configuration, to a carbon and oxygen crystal, which is, you can kind of think of as a diamond. And in that process of becoming a diamond, some heat is released, and that stalls your cooling. Now, white dwarf stars can be in binary systems, and what you can often have is your white dwarf will be in a binary system with a more ordinary star, one that is apparently longer lived because it hasn't yet finished evolving. And what can happen is if there's a close separation between these two systems, like something like an Earth to Sun distance or so, or on the order of that, then gas can siphon into a disk around this white dwarf star. And various interactions in the disk happen, and that matter is then funneled onto the surface of the white dwarf. So what you're doing is you're adding gas, which is going to be mostly hydrogen and helium from the envelope of the star. You're adding gas to the surface of the white dwarf. Because it's falling inwards, it's going to crash into the surface and release energy, so that's heat. So you're adding fuel and heat, and more fuel and more heat, and when you add fuel and heat, you get a bomb. And that's what happens on the surface of these things, is a massive explosion, many times larger than any nuclear weapon that's ever gone off on the Earth, a massive explosion that occurs on the surface. And these actually recur. You can have them every century, every 10,000 years. It depends on the system. And these explosions will just repeatedly happen, and they make a lot of elements. So they make elements up to roughly calcium. And there's a really rich set of observables for these. So you can look at these, the gas that is ejected in the explosion on the white dwarf, in this nova explosion, and you can get spectra. You can see what atoms are in this nova. There's also dust grains that we collect from meteorites that have made it to the Earth. And some of these dust grains are special because the isotopic abundances are very different than what we see on Earth. So for instance, if we take a dust grain on Earth and we compare the amount of nitrogen-14 over the amount of nitrogen-15, on Earth, pretty much every object will lie along this line. If we take the ratio of carbon-12 to carbon-13, on Earth, virtually everything falls on this line. And so on Earth, everything would be here. You can find these special little dust grains inside some meteorites that we call pre-solar grains, because their isotopic ratios are very different than what you find on Earth, and that means they were formed somewhere else in a distant system. They got trapped in a meteorite, and then they ultimately made their way to Earth. And so we have these different dust grains, and some of these, based on comparisons to model calculations, we can tell came from nova explosions. So that's another observable that you can constrain kind of what's happening on these in these nova systems. There's other potential observables that our astronomers are working on using gamma rays, using emission from rotating molecules, different things that we can potentially see. So these are pretty cool. Now, white dwarfs and binaries can also end in very dramatic scenarios that we call a thermonuclear supernova. That means that it's powered by nuclear burning, which is also called a type 1a supernova. Now, type 1a supernovae, we don't exactly know how they happen. There's two sort of competing modes, and both of them could actually be true, interestingly enough. So one is a so-called single degenerate scenario. So that's where you have just a white dwarf accreting material from a regular star, kind of like the sun. And what happens is this white dwarf gains mass because it's accreting. By the way, we don't know if they actually gain mass or if they eject more from the nova. That's an open question, but they could potentially gain mass, and eventually they'll be driven over the Chandrasekhar mass. At that point, the core will be just too compressed. Electron degeneracy pressure isn't enough. It's compressed more, that ignites the carbon in the core, and this thing explodes in a basically a massive bomb. The whole thing burns. Alternatively, you could have two white dwarfs in a binary pair, and these two things will emit energy through gravitational waves, and they will ultimately spiral inwards. And so if we follow them over time, eventually they will spiral inwards and then compress and explode. And again, you'll have a huge explosion releasing a lot of energy. So interestingly, both of these give very similar results. In both cases, what's happening is you're making a whole lot of nickel-56, and that nickel-56 will undergo radioactive decay, and you'll get some light curve, so the luminosity versus time, that follows something like this band here for some actual observational data. And in this case, you can see the contribution from radioactive decay that is powering this light curve, and different decay products will dominate over time. But kind of regardless whether you do single or double degenerate, you get something that looks like this. That's interesting and it's important because you get such consistent results for the light curve for either single or double degenerate scenario. You can use these type 1a supernovae as standard candles. You know how bright they're going to be, and therefore you can use the apparent magnitude from them in order to determine the distance. And we talked about that in the Intro to Galactic Distances lecture. And if we look at the nucleosynthesis from these two scenarios, again, because all you're doing in both cases is you're just basically exploding a bunch of carbon, somewhere between 1 to a few solar masses of carbon, the abundances that are produced are also quite similar. So if we look at the abundance versus the mass number, so this is the sum of the number of protons and neutrons, we can either compare a double degenerate scenario, the blue circles, or a single degenerate that are the red squares, and they're largely pretty similar. So working out the difference between these two is an outstanding problem in astronomy, but for our purposes for this class, it's pretty much the same. And what you make is mostly a lot of alpha elements and iron peak nuclei. So the same kind of stuff that you make in the that we talked about in the massive star evolution lecture, same kind of stuff. So while a large fraction of the iron in your blood is from nuclear reactions and the evolution of massive stars, most of the rest comes from type 1a supernovae, which is kind of remarkable. So let's switch to high mass stellar remnants. So one of the possibilities, as we talked about in the introduction to high mass stellar evolution lecture, is you could have a neutron star that's produced. So this is an object that's roughly the size of the city, and it's around the mass of the sun. So just ultra dense object, as dense as an object can get, where density has any meaning. The book says that they're a ball of neutrons. That is not true. I take issue with that characterization. It's true they are majority neutrons, but they're far more interesting than that, and the structure is far more complicated than that. So the very outer layers are made of nuclei that we actually can make and study in the lab, and this is one thing I do for my research. As you get deeper into the neutron star, you have extremely exotic nuclei, ones that we can only really theorize. And as you get to the core, we don't even actually know what the core is made of. So it's possible that it's mostly neutrons, 90 to 95% or so neutrons, and the rest protons. But within current nuclear theory, it could actually be more exotic states of matter, like special particles that are made, for instance, at the Large Hadron Collider. So these are actually quite complex objects. It's more or less the densest matter in the universe, and we're trying to understand these to figure out how matter behaves at ultra high densities. Now, because of the compactness, the surface gravity is extreme. So 100 billion times higher surface gravity than on Earth's surface. Now, a little bit more interesting way to phrase that is that the gradient in the force is also very extreme. And what I mean by that is, for instance, let's compare the force of gravity on your head versus on your feet if you're on a neutron star. So let's say your head, let's just call it 5 kilograms, and let's say you're standing on the surface of a neutron star, and your head is around 10,000 or sorry, around 10,000 meters from the center of the neutron star. So the force of gravity, this is Newton's G times the mass of our massive object, the neutron star, times the mass of whatever's being attracted here, this is our head in this case, divided by the distance squared, and this is the distance between the center of these objects. So we can plug in our numbers. Newton's G, we'll say that our neutron star weighs a solar mass. We'll call your head 5 kilograms. Again, the separation between these two is around 10 kilometers. And we get this huge number, right? Around 7 times 10 to the 12 newtons, and specifically 6.67 for this purposes. Okay, so now let's consider the force on your lower 5 kilograms. So this would be like your feet and your ankles. This is located, ballpark about 1 meter lower. It's a bit more than that, but this is just a ballpark estimate. So we can do the same calculation as above that we did for the force on your head, but for the radius, rather than plugging in 10 kilometers, we're going to do 10 kilometers minus 1 meter, which seems like a small difference, but if you do that, instead of 6.670 times 10 to the 12 newtons, you get 6.671 times 10 to the 12 newtons. Okay, it's only like a 0.1% difference. That's not very impressive, but consider the difference between these two. That means that the force difference between on your head and on your feet is 1 billion newtons. Okay? A human tendon snaps at 1,000 newtons. So this thing would snap you in two, and it would spaghettify you if you were on the surface of a neutron star. You may have heard of spaghettification before for black holes. You don't need a black hole. A neutron star is good enough to get the job done. Now, neutron stars are often rotating with a high rotation rate and have a high magnetic field, and that's going to result in a jet of radiation. The reason that they have high rotation rates and high magnetic fields is that when the star collapses, it basically captures that magnetic field, it traps it and compresses it. When you compress a magnetic field to a small volume, that amplifies the field strength. And similar to a figure skater who's spinning with their arms out wide and they tuck them in tight, how they start spinning faster and faster, same thing. You have a massive core of a star and that compresses down to this tiny neutron star. This relatively modestly spinning object is now going to be spinning very rapidly. And the jet, it can be pointed towards Earth and we'll see a signal with a repeating pulse. And so this is a cartoon here. We have a neutron star with some magnetic field. It's rotating in some way. The magnetic axis can be oriented completely different than the rotation axis, just like we have on Earth. And from the poles of the magnetic poles, you'll have this jet of radiation. And when that's pointed towards the Earth, then you'll see periodic pulsing. So this is kind of like a lighthouse pointing towards you, with some frequency. And this pulse repetition rate is extremely regular, and the way that it changes with time is relatively straightforward to predict, and it doesn't deviate from that. So these can be used as very accurate clocks. And that might sound like a fun novelty. In fact, there are a couple of pulsar clocks on Earth that are basically telescopes hooked to a clock, and that's more just for fun. But we can use them as tools in astrophysics because we have these clocks spaced out throughout the universe. And so one thing that you can do is you can look at the correlation between the arrival time of pulses for your different pulsars throughout space. And when you see the arrival time change in some correlated way, then that results in a pattern, or rather when you see a pattern in this correlation throughout space, that actually is a signature of gravitational waves. And you can learn about very distant things happening in the universe from these pulsar clocks. Another thing you can do is if you have a pulsar that's in a binary system, so a pulsar has a binary companion, for instance a neutron star, then what will happen is if that pulsar is pointed towards us, when the neutron star, for instance, is placed between us and the other neutron star that's pulsing, there will be a time dilation from general relativity. The light from the pulsar will be slowed down. And so you'll see the time of arrival for the pulse change as a function of time. And this is a so-called Shapiro delay, and this is how we can get the masses of neutron stars to extremely high accuracy. So pulsars are useful in that regard. They're also of historical interest. This is how neutron stars were discovered to begin with, and you can read more about that in the textbook. So neutron stars can be in binary systems. So much like you could have a white dwarf ultimately accreting material, you can have a neutron star there instead. These are also recurrent explosions, but they recur much more frequently, so every few hours or days, and they release more energy. So as much energy, or I should say the flux is higher. So it's as much energy in 100 seconds as the sun releases in an entire day. So you get these regular bursts. And we can compare what these bursts look like. This is the flux versus time. We can compare observations to model calculations, and in at least some cases we can reproduce these relatively well. And in doing these reproductions, this is one way that we learn how matter behaves at extreme densities. Now, one difference between the accreting neutron star and the accreting white dwarf is the matter does not escape in this case. So we can calculate the gravitational binding energy of, for instance, a proton that's on the surface of the neutron star. So this is Newton's G times the mass of the neutron star times the mass of a proton divided by the radius of the neutron star. We go ahead and plug our numbers in. We call the mass of the neutron star a solar mass. The mass of a proton is very small, about 10 to the minus 27 kilograms. We plug that in and we find the gravitational binding energy is around 3 times 10 to the minus 11 joules. Okay. Now we can compare that to the amount of energy released in a nuclear reaction in the burst. So this is the energy that would potentially power a proton escaping the surface, and it's much smaller. It's less than 1% of that gravitational binding energy, and so just none of the material escapes. So these do not enrich the universe in elements. They just are useful and interesting for studying how matter behaves at high densities. Now, neutron stars can be in binaries with other neutron stars. So just like you can have binary white dwarfs, you can have two neutron stars that are in a binary pair. So they will emit gravitational radiation that causes them to spiral inward and eventually to merge. And when they merge, you just get extremely hot material, and this material is then also ejected. Quite a bit of it anyways escapes this combination of these two neutron stars. So this in spiral and the merger itself results in gravitational waves that, as of a few years ago now, we can detect these for different systems. There are many electromagnetic signals. So you have gamma rays, you have optical, infrared, and these neutron star mergers we now know synthesize a large fraction of elements heavier than iron. They do this with a sequence of very rapid neutron captures, so we call that the R process. It's exciting because as of a few years ago, it was a possibility that this was a way to make heavy elements. As of a decade ago, it actually was even an unfavored mechanism, and now we know from observational evidence that this is actually probably the main way that elements heavier than iron are made, or definitely one of the main ways. So the key sort of smoking gun was not only gravitational waves from a neutron star merger and simultaneous gamma rays, but there's this special thing called a kilonova. And so this is an optical light curve, so you look at the brightness as a function of time here, and the shape of the light curve and the way that the color changes over time, you can use this to figure out that, for instance, we have elements like gold being made. And if you do spectroscopy here for these observations, you can also see the signature of other elements that are made in these kilonova. So, for instance, strontium we know is made. So moving on to the last remnant, black holes. These are the most compact objects in the universe. I wouldn't really call them the most dense because density doesn't mean anything here. These things are sort of infinite density, basically. Um, and the ones that are of the stellar mass variety, these are remnants from massive star death. And you can also create them in neutron star mergers. So what makes the black hole black is that light can't escape once it's within a certain proximity of the neutron star. So the escape velocity, the velocity it would take to escape the gravitational pull of an object, is larger than the speed of light. And the speed of light is the speed limit of the universe, as we talked about in the Introduction to Astronomy lecture a long time ago. So that means light can't escape these objects. If we want to describe the size of a black hole, it's a bit of a nebulous concept, but one thing we can do is we can just calculate the Schwarzschild radius. So this is the radius at which the escape velocity is equal to the speed of light, and it's roughly 3 times the ratio of the mass of the black hole to a solar mass. So for instance, if I have a 1 solar mass black hole, then the Schwarzschild radius is around 3 kilometers, 2.95 kilometers. If I had a 30 solar mass black hole, then you'd be at around 90 kilometers for your Schwarzschild radius. When we look at the mass distribution of black holes, there's an interesting gap in that distribution between the masses of black holes that we observe and the masses of neutron stars. So the vertical axis here is a sort of log scale of dense objects. The green dots, these are all observations of neutron stars, and the red band indicates the uncertainty. The black dots are neutron stars, and the red band indicates their uncertainties. And these funny gray connecting things, these are objects. This is, for instance, black hole mergers forming higher mass black holes, or in one case here we have a neutron star merger that we know has formed a black hole. You'll notice, though, that there's nothing in this region here. So this is called the black hole mass gap, and we still don't exactly understand why this gap is here and how far the gap should be. We don't know what the highest mass neutron star you can have, and we don't necessarily know why, the details of why there's this gap here, which is kind of cool. So black holes can also be in binaries. You're seeing a theme here. You can have accreting black holes, and this is one of the main ways that black holes are discovered. Because the black hole is black, it's not giving off any light. It's usually kind of the absence of light in a sort of bubble region around where you have other light being emitted that you can sort of see these objects. You also get X-ray emission from accretion onto the black hole, and so X-rays are emitted from the accretion disk, and the reason that you can see that is that's emitted outside the Schwarzschild radius, so light can still escape, and that's one way that we see black holes. Now, finally, black holes can also be in binaries with other black holes. So this is more or less the same idea as our merging neutron stars and kind of like the merging white dwarfs. But in this case, there's only gravitational wave signals. Nothing else is going to escape. You have 2 black holes, nothing can escape those, so that's it. There's just gravitational wave signals, which might sound a bit boring, but this is one way that we can now, within the past handful of years, probe general relativity, which is sort of the study of space-time itself. This is a way that we can study this and test general relativity in a way we were never able to before. So we're going to play a movie here that hopefully won't mess with the audio of my recording. What we're looking at here is 2 black holes. They're indicated by the black objects. We're going to see these colors are sort of the deformation of space-time, where blue is less deformed, red is more deformed. And in the bottom, what we're looking at are the gravitational wave signals that come in as a ripple, and then when these 2 things merge, you're going to see a ringing. So let's go ahead and watch this. There's a counter in the upper left part of this video counting down to the merger. So these 2 black holes are warping space-time quite a bit in their local region. That's why there's the red divot there. And they're spiraling around each other. And they're creating some ripples in space-time if you look in the distance that are a little bit hard to see at this point because they're not particularly big ripples. These two things are emitting gravitational waves and they're spiraling inwards, and if you can probably tell now they're getting closer and closer. Those two divots are coming together. And then ultimately these two divots are just about to merge. So this is slowing down to show you the detail of the last sort of bit here. You're looking at the ringing down on the gravitational wave signal on the bottom. These two things are combining, and this is where they finally merge. So you look at the wave signal on the bottom, you get that kind of ring down, and then now in the background you see these blue and pink things. That means there are big ripples in space-time, and these are the signals that can be picked up by a gravitational wave detector such as LIGO. And this is a pretty exciting tool that we now have to study matter in really extreme cases and gravity in its absolute most extreme state. And that is it for this introduction to stellar remnants for Astronomy 1000.